Yes, okay, so I'm Stephen Chenney, and this is Ian Vollick, and we're going to talk about Slimming Paint, and the first slide is important, so actually let's just go to the first slide. The first slide is, this talk is about caching our paint recordings, our data about what we're going to paint, so that we can reuse unchanged drawing commands, and it's also about changing the organization of the code to move layering decisions, that is, what gets drawn into what texture on a GPU, what content appears on top of what other content, into the compositing system and out of Blink. Why do we want to do this? Well, re-recording is expensive. I'll show you how in just a minute. And Blink really shouldn't be doing layering. Blink does not know anything really apart from what needs a layer, but it doesn't know about how to assign those layers. It doesn't know how many layers you can support. It doesn't know how big layers can be, how much memory you're using, or anything like that. So this talk is going to go through all of this in more detail. So to give context for this, we realize that a lot of people may not know sort of what painting is involved. The current, in some sense, from getting a page or from getting a new frame or getting some change from JavaScript to getting it on the screen looks like this kind of pipeline. So the network and parsing does something, at least for page load. Then you've got some DOM manipulation or DOM change. You do some style update if necessary. You do layout if necessary. So DOM figures out what it is you're dealing with. Style figures out what properties apply to any given object on the screen. Layout figures out where everything is and how big it is. The compositor setup then operates to figure out which objects should appear in which depth layers. So what should be on top of what overlaps what. And then the compositor then comes back and asks Blink to record or to paint into each layer. So for the background layer, what should appear there? Please give me the drawing commands for that. Then give me the drawing commands for the next layer, and the next one, and the next one. And then off to the right of this slide is the system, the actual compositor thread that then takes all of those layers and puts them on the screen using graphics hardware. So this talk in Slimming Paint is about the last two steps there, where there's just really too much fat, and in fact, where it's backwards. After layout, we should do painting and recording, and then the compositor should do compositing setup. There's no reason, well, the information is in the wrong place. At the bottom is a trace there, and what we're talking about is everything from here through to here. Okay, so everything from this is layout code here. This is assigning layers. This is recording drawing commands. And then off to the right.
Steven, about a third of your time there is spent locked. Is that typical? Is that just random in this sample?
I cannot answer that question for this particular sample. So you're saying for update layers, we're blocked a lot?
Oh, it's just the whole trace.
Yeah, but so half of it is here, and half of it's here, and it is random. Yeah, this came from out of some sequence related to Dimitri's polymer performance slides. Yeah. So the reality is that this can take. So this is. The reality is that well, I'll go to the next slide. so basically, this is some frame where we actually spend far more time issuing drawing commands than we spend doing layout or style. And in some sense, once you've done layout and style, it should be really easy to you've got all the information you need. You should just be able to spit out all the drawing commands. So, like the whole point is you've done layout and style, you've figured everything out, you should just be able to draw it. It shouldn't take longer to issue these drawing commands than it takes to figure out what you're going to draw in the first place. Right, and so if you want a bit of a better understanding, exactly how big these things are depends on how much you change on any frame, how big the damage rectangle is, how much stuff overlaps the damage, how much content gets changed. All of these things affect what these frames look like. Okay, so the project goals of Slimming Paint, three main goals. One is record and paint faster. Second is do compositing faster, and more importantly, do it correctly. We're going to show you an example where we, in fact, generate the wrong output. The thing we show on the screen is not correct, and we cannot fix it with the current architecture, or at least not easily. And finally, our goal is to produce healthier and better code. In particular, better testing, code that more directly maps onto sort of the logical systems that that the code's implementing. So the painting bottlenecks, the key areas that we want to attack is layer management, expensive layers. So if you're familiar with the sort of internals of these systems, render objects, the render tree generates render layers generate graphics layers generate some other kind of layers in the compositor, which then go to something else. And so all of these layers are transformations that don't really need to happen. We really only need one representation of what layers are. And this is just, all of this is expensive. Secondly, Blink's paint code is not optimized for our current system. From WebKit, we inherited essentially two code paths. The original compositor work was done on top of core animation and core graphics, and that has a particular behavior pattern, a particular set of APIs. And our current system, and in fact, the implementation when we're back in WebKit is built on top of Skia and CC. And so we needed to jump through a bunch of hoops, basically, to make core animation, core graphics kind of constructs map onto our preferred architecture ourselves, right? So Compositor in a separate thread, Skia as a drawing backend, all of these kinds of things. And the final thing the final bottleneck is that at the moment we cache pixels when we can. So the Compositor will maintain all the pixels in a particular layer to enable fast scrolling, for instance. So if you're just scrolling, you don't redraw the contents of the layer, you just move the texture up and down. So we cache pixels. But anytime anything changes, anytime we have to redraw some portion of the screen, we repeat any work to define what those pixels should be over and over again, even if only some small part of it has changed. So we're doing too much. We're sort of caching at the wrong level. We're maintaining state at the wrong place. So to give you a sense of how much scope there is here for code reuse, for the image case, I actually looked at this in detail. Instrumenting the draw image call inside render image when you actually paint an image, it's like, I believe it's more than 80% of the time. Unfortunately, the numbers don't appear in any email I can find. Nothing changed at all. We are calling draw image with exactly the same parameters that we called before. We're checking the image exists, we're updating its interpolation properties, we're resizing if necessary. We're doing a lot of work for no benefit whatsoever. We could have just sent exactly the same data. We could have reused exactly the same recorded call for how to draw that while doing none of the setup operations at all. And given that reusing it at some point was taking about 1/20th of the time it took to actually redraw it, there's a huge potential here for speeding things up. And there are many cases like this. We do this with text, which is also even more expensive to set up. We do this with lots of things. Okay, so I'm going to hand it over to Ian to talk about why compositing is broken.
Thank you. So as Stephen mentioned earlier, our current architecture makes it impossible to composite the way we would like to in certain situations. We composite currently in terms of render layers. If you haven't got a render layer, you're kind of out of luck. And that causes a fair bit of grief, actually. The atom is just too big. It causes the fundamental compositing bug, and I'll describe that in detail in subsequent slides. But it also prevents us from doing things like accelerating parts of an SVG. It would be nice if you could unbundle it and put separate bits of it into layers and composite and stuff, but you just can't because we didn't happen to have the render layers lying around to do that with. And it's also, as Stephen said, a layering violation. And what I mean by layering violation is that we're making decisions at the wrong stage in the pipeline. So Blink isn't best equipped to make decisions about what should go into which composited layer. It might depend on your hardware, say. It might depend on, how we're going to raster in the future. And every time you make a change to the compositing backend, to go and teach Blink how to do this is really a leaking of concerns into Blink that's really kind of unfortunate. So we would like to move those decisions to where they're more appropriate. And also, it's proven over time that it's not a very flexible architecture. So when we wanted to do things like squashing, and squashing is taking composited layers and combining them, that ended up being a retrofit on the system we would promote. We would decide that some of those promotions were bogus and we would unpromote, and then the origins of certain layers would be wrong now because you're sharing a layer with other people. It was tricky, very complicated to retrofit the thing, but if we'd been compositing in a way that was more natural, some of these features might have been easier to implement. So I'm going to talk a bit more about what that fundamental compositing bug is. So say we've got one composited layer. It's this thing with the orange border here. And we've got all of this content painting within it. We've got this green thing that's underneath the blue thing. But say we're gonna promote the green thing, right? But that thing that's blue doesn't have an associated render layer. Well, what'll happen is the composited thing will pop out into a separate bucket of pixels, which will necessarily be on top of the other bucket of pixels. But the blue thing will continue to draw into the back one for a couple of reasons. The first reason is that it doesn't participate in our overlap detection. So normally we would correct this by saying, oh, you overlap the thing we promoted. We better promote you above this so that you can stack correctly. But it didn't notice. And even if it did notice, it doesn't have the machinery just architecturally to have all the composited stuff wired up to it. So this is a drag. And just to prove that it's real, here's a more concrete example. I mean, it's got ellipses in it, so it's not fully baked, but it's mostly baked, of a case that is almost exactly what I showed you before. So we've got a canvas here with a red background. It's in the back. And we've got a div in front of it. We've margin topped it up so that it slides underneath the thing that's above it there, which is kind of sneaky. So this thing, this div here is should be below it, but what we see is, oh, wrong direction, that. So the red thing popped on top, which is bad, that's broken stacking. And why did it happen? Oh, this is a statement of why it's wrong. The canvas got its own backing and it popped on top, but the div shares the body's render layer, so it paints in behind it, which is a real drag. And this restates what I said to you earlier. So I'm going to just skip right over that. All right, I'm going to hand it back to Steve at this point to talk about code simplification.
Right, so the final goal of the project is to try and simplify code. And as I said, the most important aspect of this is to better match the code into the logical units. So that Blink will do CSS painting algorithm, all the necessary phases as described by that algorithm. The graphics layer logic will appear in the compositor. So the compositor knows about hardware. It knows about all the things. I mean, it knows everything you need to know to actually determine how many layers you want, which layer, what the layer size, what the resolution, which things are going to scroll, what isn't. These kinds of things the compositor knows. As a sub effect of this, we'll be able to remove some stuff, and we'll also rationalize the way that we do hit testing. For instance, there are opportunities to improve other aspects of the system that interact with where things are on the screen. So the second part of simplification is to rationalize the paint phases. I don't know if you ever dig into the code of how we go from I want to fill these pixels to a method that actually draws some rectangle. We go through several transformations of what a phase means and different layers of code that all manipulate this phase and manipulate the coordinate systems in the rectangles. And we'd like to rationalize this. We'd like to be able to say, just paint whatever you need to paint to fill this space. And the Blink, which knows about what the phases are, should be able to just paint that stuff. We also will simplify the code by compositing on the right data structures. So because we came from a core animation compositing background to some extent, and because we needed to do transformations of data structures to get into something that our compositor can understand, the compositing is currently operating on a structure that isn't optimal for making the decisions and doing the operations that it needs. So by cleaning up the data structures in the course of this project, we should make the compositor a lot simpler, just because the representation will better match what we need to do with it. This also applies to certain other things, like overlap testing should be easier. There are even opportunities here to simplify the way that we talk to skier and deal with caching, with culling rectangles and bounding rectangles and these kinds of things. There's lots of opportunity here to match up these data structures. Okay, so that's sort of what the goals are. I'm going to talk a little bit at a reasonably high level about how we're going to get there, or how we expect to get there. So first of all, what code is affected if you're working in Blink? Which areas are sort of going to be changing a fair bit? The first one is Blink painting code. So anything that any render object or many render objects have these paint methods: paint something, paint contents, paint border, paint background. All of these methods are being broken into their own directory, not a different compilation module, but a separate directory containing only painting code. And the painting code itself is going to change from generating a single SK picture, a single recording of what is painted on the layer, into generating a list of painting items. So I'll show you what this list looks like. The compositor will be affected, very significantly. The input to the compositor will change from being a graphics layer tree into being this list of things, and it will need to take on the responsibility for doing all the things that Blink currently does in generating these trees. And then the rasterizer we think will be affected at some point. There's no direct plans yet, but there are opportunities there to improve texture management, to take more to pay more attention to what GPU you're running on, and other changes to rasterization. So the top level design in Blink is that Blink Paint will produce a list of display items. So you'll call paint on on the set of invalid render objects. You'll generate a list of things that need to be displayed and a list of hints that tell you that are important for controlling the display. So you might put a transform thing in this list, or you might put a clip in there, or you might put some hint that this is a scrolling thing, or any number of things might appear in this list. The compositor will consume this list and produce layers, and then we take what appeared in the list, rasterize it into the layers, and send it to the compositor to put on the screen. Part of the top level design is this ability to reuse, and the way we plan on doing this is that when you invoke paint, you'll only look at invalid renderers. So we know from style and layout calculations which objects actually changed. Only those objects will paint. So only objects that are known to change will generate new pieces of display list. We'll have a merging algorithm which takes the old one and the new one and puts them together to generate the current complete list. That goes into the compositor, which will take the old list, the new list, and the previous layers, figure out which layers have changed and which ones haven't, and only re-rasterize the layers that have changed, and then again off to the compositor with a new set of layers. There's a few things that are important in this picture. The first is that if we don't regenerate painting list items, we can tag those as, it makes it beneficial then to have long-lasting persistent IDs on these paint items, so that subsequent systems, in particular Skia or any other system, can know that this is the same thing you saw the last time. And this enables various optimizations further down the pipeline. If you know what you've got is the same as what you had before, it at least opens up the possibility of reusing it, even if reusing what you had before. You don't have to reuse it, you can always regenerate it, but at least you now have this option. Previously, all you got was this big long list of commands, and you had no idea whether the time it would take to figure out whether that was the same thing as what you drew before was just not worth the effort to try and do so. So now we can deal with persistent objects. Okay, I think that's all I want to say there. So what's currently changing is what's already happened. I don't know I think this is actually complete now, or almost complete, is that all of the painting code has been moved out into this other directory. So render object now creates a painter every time it wants to paint. The painter goes through, executes the paint code. This is a fairly minimal refactoring, mostly just moving stuff around, although we did find some places where stupid stuff was being done that we fixed. Subsequently, we want to take this and rearrange it in order to make it easier to understand what's going on. In particular, we want to break out the code paths per phase, so it's clear which pieces of painting operation apply to which phase. This will make it dramatically easier to debug stuff, right? If the background doesn't look right, it will be clear where the background's being drawn. Right now, this is not obvious. It will also better map the CSS paint spec onto the code. So any changes to spec, again, any bugs or fails of compliance we can look at, we can more easily track. So that's the long-term goal there. The changes to outputting a display list are currently in progress. So some stuff has been changed, some stuff hasn't. There's actually a flag. I'm sorry, I should have put it on the slides. If you enable slimming paint, is that right? Yes. So if you enable slimming paint, you'll get this code. You'll get this code path that outputs display items, but it will not work at all. You might pass like some tests, 20, 30, some small number. 490. Oh, okay. We passed 490 tests currently. So as we move more and more of the code over, obviously more and more of the tests will pass. But really, this right now is exists so that we can enable the path and work and develop with it. You can also turn it on in layout tests, and so it makes it possible for us to make sure we're doing the right thing. So this is mostly in flight. We have not yet really dealt with the only invalid renderers generating new data. That's just starting to land now, and the merging step is just starting to land. Right, and so the only regenerate invalid data and doing the merge, the post-paint merge, is just starting to land. But did you get it in, Philip? Yes. Okay, it is there. This is how new this is. We don't even know what we've landed. So just as a concrete example of what this list looks like. So for instance, we've got a div with a clip, and we're drawing something, and we're using the papaya whip color, which San Francisco office might know something about. So the output from this is a begin clip and an end clip. The reason we need to bracket clips is because, well, you need to know when you started it, you need to save some state, and you need to pop some state. So we need both begin and end. We then fill the rectangle, that is the rect for the div. Then because happy is a child of the div, we should draw that afterwards. So we draw the happy background, we draw the happy foreground, and we end. So this is a concrete example of how some code, some CSS and DOM may map onto the drawing list. Obviously, these will get dramatically more complicated. Transforms don't appear anywhere here, for instance. They also need to be bracketed. And all of the hints that we currently use to set up layers, so things about opacity or stacking context, z-index kind of stuff, all of these things need to appear in the list so that the compositor knows how to layerize. And then moving further forward, the plan is to get rid of graphics layer. The intermediate goal, once we've got paint lists going, is to get rid of graphics layer and the composite layer mapping. There was an awful lot of pain trying to make composite layer mapping faster. It got a lot faster, but we'd like to get rid of it entirely. The reason we want to get rid of these is because, again, these are Blink's trying to do work that Blink doesn't know how to do. The compositor is the thing that knows about layers. It should be the thing making layering decisions. And then once we've got rid of that intermediate step, we'll go and hopefully get rid of render layers as well entirely. So each object will issue the commands it needs, and we'll figure out from that command stream which things need to be in what layers. This is where, for instance, the various bugs with SVG and opacity and foreign objects and stuff all get fixed. In other words, things that don't have render layers right now and do the wrong thing will, in some sense, not need render layers to do the right thing. Okay, back over to Ian.
So changes to the compositor, exciting. So I guess before getting into CDP and explaining what CDP is, I should emphasize that what we currently do is we take the render layers and we figure out what to promote and make a tree of graphics layers, and then make another tree of web layers and turn them into web layer impls and CC. We have a zillion trees, right? And to figure out all of the draw properties required to actually display these things, we do this big function called calculate draw properties. It's very big, and it walks the full tree. It computes things like every layer's full screen space transform and whatnot. And we think that we're going to be able to replace it with something that's a little bit simpler. So we're going to get from Blink now, not just this tree of layers, we're going to get just a list of paint operations, and we could move to a list of layers with tiny trees for example, your transforms. So whereas before, everybody needs to know what their transform is, now you can say, well, I'm in the space of my transform parent, and I'm a 2D offset from it. And we posit that there are not many significant transforms in this tree. They're going to be on the orders of 10, 30, 100 of them rather than a gajillion. And we would get them for things like clips. If you're animated, you would get one of these, right? Stuff that you might update from frame to frame. Right. So that's what we're hoping to get rid of and move towards. There's a lot of detail here, and I'm not going to get into it in too much depth because it's a little bit dry, but if you're interested in it, I'd be happy to chat with you afterwards. So please contact me. I'm going to switch on to the next slide. Right. So I'm going to briefly describe sort of how layerization will work in the compositor in this new world order. So as Stephen said before, Blink will emit this list of display items, and some of them will be hints about layerization. For example, these things are clipped together, or these things are transformed together. And as we scan through the list, we can cluster groups of them and stick them into composited backings here. Now, something that's not captured by this slide, but should be emphasized, is that we can do squashing at this level. We could, for example, say, well, what is the furthest back graphics layer I could squish these things into? And we could squash here. And it's a lot simpler to do squashing at this level than it was in Blink, where we had to promote everything and unpromote things and then change the space of everything. Here, we just sort of move things into a further, you know, behind the camera backing. Right. Oh, something that we're going to have to do for the near term and possibly forever is to do a translation step. The Compositor has some other clients, the Chrome OS UI, for example, speaks to it in terms of layers. So we're going to have to take those layers and convert them to the new data structures that we would like to speak in terms of. But it'd be great if they could speak, you know, our new native tongue. So hopefully in the future we could switch them over, but we may be doing this translation for a fair bit of time in the future. Yes?
Does this change at all the vision of work between the processes?
The question was, does this change the division of work between the processes?
So for example, are we moving from the renderer process to the GPU process?
No, all of this work would still be done in the renderer process, so no, it does not. Yeah. All right. All right, I'm going to pass it back to Stephen for.
Yeah, so and just while a lot of this work is called compositor work, it was not done in the compositor or GPU thread. It was actually done in the main render thread, and so it's somewhat compositor lives in 2 threads, and all the work we're talking about here is actually done in the renderer thread. Okay, so we want to be able to measure whether we've succeeded or not. We're talking about a really big change here. One reason that we think we can succeed is that this is what other browsers actually do already. So there's clearly a way to do it, to make it work. As far as measuring success, we want improved frame times. In other words, we want to go faster. We think the place we can go the most fastest is with dynamic content. So content where you're changing something but not everything. So you've got a slider that's coming out, or you've got links that are highlighting, or little UI elements that are popping up as you mouse over them. These kind of situations we should be able to be dramatically faster. We'll also succeed if we can composite more content. So if we can move more stuff to GPU layers that don't change, that we can cache, or that for whatever reason we can get more performance out of the compositor. And the actual metric will be developing more telemetry tests to try and get a handle on these things. Our current telemetry set does not necessarily stress the kinds of behavior that we're seeing, either because that's not large enough or because it animates, it's changing everything at once. It's not going it doesn't really refine these cases that we think we're going to improve the most. We'll succeed if we reduce the bug count. Right now we've got bugs that have been open forever that we cannot fix. So it would be nice if we could actually fix those. And in the long run, we hope that this produces fewer bugs. It's just less complicated in theory. We should make fewer mistakes. We'll find out. And then we'd like to increase our own productivity. Right now, it's horribly complicated. The time to ramp up on a system like this is extremely significant. It takes a lot of people to know different bits of the system to get anything done. And we'd like to make things simpler. There's a few related projects that are also attempting to do sort of similar things in different areas. There's a project called Text Blobs, which is computing text painting information once, as opposed to the 3 times that we currently compute it on the way to getting it on the screen. And to generate it once in layout, pass it all the way through the system to Skia, and Skia knows how to draw these things very efficiently. So this will speed up our text rendering in particular. It's also already landed behind a flag. And on text-heavy pages, this generates sort of multiple percentage points, 10% speed up in terms of painting. It's a significant improvement. Also related is the GPU rasterization project, so get all content being rendered on the GPU. It relates to this because we have an opportunity to modify the kinds of inputs we provide to the GPU, the kind of information they have to perform GPU rasterization. And then there are various other perf projects that are going on, also trying to reduce some or other aspects of this. Okay, so the people involved, tech leads on Blink is Chris, who's over there. You saw him this morning. compositor is Ali, who's somewhere waving back there. And there are a few people on each team working on making this happen. If you have questions, they are the best people to talk to. Yeah, although Ian and I are also certainly available. Okay, if you'd like to follow along, we put out notes from weekly meetings and any significant development discussions on Silk Dev. So this is the Silk project is the primary performance-related project inside Blink. And so notes are going out to there. We should be, I don't know that we actually are, CCing all our reviews to Slimming Paint reviews. There's an overview document that's linked here. I presume the slides will be available if I send them to someone. And there's a wiki page, but that really just has another set of links to these documents. So the main, I did update the overview document. It does vaguely reflect what our current thinking is, as opposed to what it was 4 months ago. And I think that is the last slide I had. Yes. Does that last Go link, does that work if you are not? Yes, I was going to say yes. If you're a Googler, the Go link will work. Otherwise, it's on the Chromium wiki site, and I don't know how you find things. Yes, the link on the slide is the full link. Yes, that's right. Any questions, folks? Yes. Sorry, say that again. I missed the. Still missing it. Oh, okay. So, right. So the question is, how does invalidation work within the Slimming Paint world? Right. So, so we still think that we'll get invalidation rectangles the way that we get them now. But when those rectangles go back into Blink and it's asked to fill in those rectangles, it will know which objects in that rectangle have actually changed and which ones haven't. So right, so it will change. It's not entirely obvious exactly how it will change, but we should end up reissuing. We should end up doing less work per rectangle invalidation than we currently do. In particular, right now you invalidate an entire render layer, and everything in that render layer in that rectangle gets repainted, it reissues all its draw commands, and that will change. The only things in that render layer that actually changed will reissue draw commands. Yep.
So right now it's sort of difficult to know exactly what regions of the frame have been invalidated in the browser process. So will we have access to the invalidated regions in the browser process when we draw that new frame?
If you want it, we might be able to get it to you, but there's no plan to ship it to the browser process as far as I know. You're talking about like the UI browser process?
Exactly. And so the use case is if we're putting that surface somewhere else. So for example, if we're putting on a remote device and we only want to repaint the portions that have changed, it would be nice to have both the complete positive frame and also information about the specific regions that have been modified.
Okay, so the question is for case, so to restate that for everyone, the use case for the browser having access to the repaint area and invalidation rect is that the browser process in many of the use cases we have now is sending the frame to some other thing. So I presume we're talking about Chromecast and things like this. Yeah, so so can we get the invalidation recs to you? If you need them, I think we certainly can. The Compositor has them, and they could come back with the frame, I presume. Yeah. Right. So the statement was that there's some support inside the drivers now to get these partial updates. So you're saying it reports back the rectangle that was redrawn?
It goes from Compositor to delegated Compositor and goes all the way back to EGL driver.
Yeah, okay.
And there is a media extension that works on video. On the video EGL and the name of the
Okay. Yeah, should take any more discussion of that offline. Yeah. Okay. Yes.
So this might be too like dumb for this discussion, but the fundamental compositing bug, since it's web exposed, are we not concerned about content that depends on that?
So Adam's question was, and correct me if I'm rephrasing it incorrectly, if we fix the fundamental compositing bug, are we going to break sites that depend on the fundamental compositing bug? There is a possibility, yeah. Situations where we get where we do expose this are like if we have a composited iframe, like the contents of the iframe are composited, or if you've got composited scrolling, for example, and we promote those things automatically, and the automagical promotion of that thing can cause things to stack incorrectly. The hope is that that will break few sites.
Is there evidence of that, or is it because other browsers don't have this bug?
Wishful thinking. Do we have evidence?
Yeah, so Firefox is getting the exact same problem that we have, and they fix it with the hate list just like we are doing, and they solve it with nothing but in the same way. The WebKit shares this one with us. So your point is good status.
Yep.
Can you repeat that?
So what PDR said back there was that Gecko fixed the fundamental compositing bug in exactly the same way, but we share the fundamental compositing bug with Safari. So there is a real concern about having differences in painting order. Yeah. Can I delegate the answer to that question to PDR? Just come up here.
You can ask the question as it's coming up.
Okay, so the question was that merge step where we merge display lists looks interesting. Do you have any idea what the complexity of that is?
Order length of the display list. We have a doc that describes how it happens. Basically, we reuse the existing display list, the order that it provides, in order to make this fast. The doc goes into detail about it, and the patch landed last night around midnight. So that's how like new this stuff is. But we think we're going to be able to pull it off.
I think that's a wrap. We'll be available afterwards, obviously, and I think the next talk starts at 3:30.
Cool. Thanks, guys.